So we turn now to the contribution that Boltzmann has made to this question of the calculation of the distribution of energy within levels of a molecular energy structure. And we know already that Boltzmann gave us this crucial relationship between entropy and the number of microstates. And we derived the explicit form for the calculation of entropy from a microscopic point of view, that is from a molecular point of view, using that relationship. Another very important contribution that Boltzmann made was the determination of the relationship between an energy level J and all other energy levels in a molecular structure. And in fact, the crucial equation that we derive from Boltzmann's work was that the number of molecules in energy level J divided by the number of molecules in energy level I, where energy level I is below energy level J, that's equal to e to the minus the energy of energy level J minus the energy of energy level I, all divided by K times the temperature. Now that K is in fact the Boltzmann constant. And that was another reason, in addition to the fact that his representation of the entropy in terms of a constant, both turn out to be exactly the same constant, and they're named after Boltzmann for a very good reason. So the question we want to address is to determine the fraction of molecules above a certain level J in a molecular structure. That is, we want to know the ratio of molecules above a certain energy level E sub J relative to the total number of molecules in the system. So to do that, we turn to the Boltzmann distribution of molecular velocities. Now this is so common in the discussion of chemistry and the physics of molecules is that it's referred to as the Boltzmann distribution. And this comes from the development of statistical mechanics, for which Boltzmann was the father of all of this, and it was a brilliant contribution. And whenever the term Boltzmann distribution is used, it means we're plotting the fraction of molecules in an ensemble of molecules against the energy, in particular the kinetic energy of the molecules within that ensemble. And that has a very specific functional form. And again, in our quest for determining the fraction of molecules above some level J, we're looking for the number of molecules in the high energy tail of that distribution relative to the total number in the mix. So we can write that as N at level J or above divided by the total number of molecules in the system. And for the Boltzmann distribution, that is the fraction of molecules versus energy, it's equal to e to the minus the energy of that Jth level divided by the Boltzmann constant times the temperature. Now we know that the Boltzmann constant applies per molecule. If we want to apply this to the condition for the number of moles, then we have to write this as e to the minus e, and it's called the activation energy, E sub A, divided by the gas constant times the temperature. So this is per mole, and with the Boltzmann constant, it's per molecule. Now this has a tremendous amount to say about the rates of chemical reactions, because as you know, when we initiated chemical explosions, we had to use a flame or a laser or a flow of electrons to initiate that reaction. And we can see exactly why that is, because if we plot the energy of the Boltzmann distribution against the activation barrier for a chemical reaction, it's those molecules above a certain value, the activation energy, that can clear that barrier height. So there's an intimate relationship between the initiation of a chemical reaction and the Boltzmann distribution, and that's why it's so important.